All right, quiz 6 solutions for Math 252. The first problem, I ask you to take this integral, which I changed, by the way, to make the numbers work out a little bit nicer. And you stare at this and you're like, I don't know how to take this integral, but I could rewrite it in a different form so that I would know how to take the integral of what I was left with. And the way you write it in that different form is by using what's called partial fraction decomposition. So the idea with partial fraction decomposition is you first factor the denominator, which is already done for you, as I promised it would be. And then, since these are both linear factors and they're not repeated, you can rewrite this as just a sum of two different fractions, where one of them is some constant over a plus 1, and the other one is some constant over 2x minus 3. And if you could just solve for those two constants, then what you would have here is something that you could take the antiderivative of. But before we start worrying about antiderivatives, let's solve for the constants. So the way to solve for a and b is what's called clearing the denominator. So multiply both sides of the equation by x plus 1 times 2x minus 3. Kind of think about those as up on the tops of all three of these terms. So if I have an x plus 1 and a 2x plus 3 up top up here, they'd cancel with the ones on the bottom, and I'd be left with just x minus 9. If I have an x plus 1 and a 2x minus 3 here, the x plus 1s cancel. So I'm left with just the 2x minus 3 times the a. And then similarly over here, the 2x minus 3s would cancel, and I'd be left with just the b and the x plus 1. And so what I got to do is find values of a and b that make this a true equation, which if you're really clever, you might be able to just figure it out. You know that I always pick small numbers. You might be able to do it without going through these steps. But what you're supposed to do is first get rid of the parentheses. So I got 2ax minus 3a, and then I got bx plus b. And then what you want to do is what's called equate the coefficients. So you look at your x's, and on the left-hand side of the equation, you just have 1x. But on the right side of the equation, you got 2a and then b more x's. So what that means is that 2a plus b must be the same as that 1. And then equate your constants. So you got negative 9 on the left side, but on the right side, this negative 3a is a constant and this b is a constant. So you got negative 9 equals negative 3a plus b. And then you have these two equations and two unknowns, which you can solve however you want to do it. I did a video where I did these by substitution, and I also, in the video, showed you how to do this by adding equations. In this case, I think adding them is a little bit easier. Maybe we could take this bottom one and multiply everything by negative 1. That would give us that 9 equals 3a minus b. And the reason I wanted to multiply those by negative 1 is because I kind of looked ahead, and I knew that in the next step I could add the two equations together. And if I multiplied these by negative 1, then my b's would cancel out when I added the two equations together. And that's really nice because that'll just yield that 10 is 5a. So then I can solve for a and get that a is just equal to 2, dividing both sides by 5. And the second that you know that a is 2, you pick wherever you want, I don't know, maybe here, and say that 1 equals 4 plus b. It sure sounds like b is negative 3. And then once you have these values for a and b, you can come up here and be like, yeah, this integral you wanted me to figure out here is the same as the integral of 2 over x plus 1 plus negative 3, I guess, or minus 3 if you'd rather write it that way for this negative 3. Over 2x minus 3. And this, unlike the original question, is fairly easy to take the antiderivative of. Think about it as two different terms to take the antiderivative of each one individually. For this one here, you could pull the 2 out in front, and then you would have 1 over x plus 1. And the antiderivative of 1 over x plus 1 is just the natural log of the absolute value of x plus 1. You can do a u substitution there if you feel like it. And then for this next term, you want to pull the negative 3 out in front. And then what you'll have left is 1 over 2x minus 3. And here, if you're thinking that the antiderivative of 1 over 2x plus 3 is just the natural log of 2x minus 3, you're close, but you're not quite right. And the idea is if you took the derivative of this guy, you'd have 1 over 2x minus 3 times 2 for the chain rule. You'd end up with an extra 2 because there's a coefficient on this x. So to account for that extra 2, you got to throw a 1/2 up here because you don't want the extra 2 when you take the derivative of this guy up there. Tack on a plus c and you're essentially done. You could leave your answer like this, but I don't like the way this 3 times 1/2 looks, so I'm going to rewrite it as 2 times the natural log of the absolute value of x plus 1 minus 3/2 natural log of the absolute value of 2x minus 3 plus c, and call that good. So I think this problem will be a little bit more fair for you guys to take on. Still not super easy, but hopefully this one will be manageable. The way I think that would make the most sense to attack this one is you stare in the denominator here and you see the square root of 25 minus x to the 4th. But then you go down here and you say that these are all forms involving the square root of a squared minus u squared. So this u squared right here must have to be this x to the 4th power. Well, in order to make that work, I'm going to need my u to be equal to x squared. Because if u equals x squared, then u squared is x to the fourth power, and so this will be my u squared. But if u equals x squared, then du is 2x dx. So now you got to think about how to make all the pieces fit. I mean, this 2 is not an issue because it's just a constant. I could say half of du is equal to x dx. But if you look up in the numerator here, you don't have an x. You have x to the fifth power. So what I'm going to end up doing is I'm going to think about this x to the fifth as x to the fourth times x. And the x to the fourth will change into a u squared, and the x will get sucked up as part of my du. So what I'm saying is when you do all the substitutions, you'll end up with a 1/2, this one out in front of the integral. And then up in the numerator, you'll be left with u squared. And down in the denominator, you'll have the square root of 25 minus u squared. Du, because I've switched my variable of integration. And I think this is going to fit one of the forms pretty well. U squared divided by the square root of 25 minus u squared. Let's see, that looks a lot like this guy, right? Number 34. I think it's exactly number 34, except instead of a 25 in the denominator, there's an a squared in the denominator. So it sounds like a must be equal to 5 because it can't be -5 because a's are greater than 0. So what I'm going to do is I'm just going to copy exactly what I see from number 34, except I'm going to change the a's into 5s and the u's into x squareds. So 34 says I got negative u over 2 times the square root of a squared minus u squared. So here's my u over 2, square root of a squared minus u squared. And then I want to add to that a squared over 2 arc sine of u over a. So here's my a squared over 2, and here's the arc sine of u divided by a. And I don't know, this is probably acceptable, but it's a little bit ugly. I would either distribute the 2's back in or maybe pull the 2's out. So if I pull out the 1/2 from each of these terms, it becomes 1/4, and now there's just an x squared here and a 25 here. And note that I put the c outside the parentheses because 1/2 times a constant is just some other constant. And so that ends up being the answer for this question. Before I call this good, I'm going to do this problem, which I changed to make it extra credit because I think it's pretty hard. It's kind of similar logic to what we did over here, where you see the 9 minus x to the 8th power, and then you're like, well, the u must be equal to x to the 4th power because I need this to be a squared minus u squared in order to use these tables. But if u is x to the 4th, then du is 4x cubed dx. So a fourth of du is equal to x cubed dx. But you don't have an x cubed dx up top. In fact, it's even worse. You got an x to the 5th down in the bottom that you haven't taken care of. But look at this little trick. If we pull the -7/4 out in front, we can rewrite this integral as instead of x to the 5th down on the bottom, x cubed up top and x to the 8th on the bottom. And you're like, how would you ever see to do that? You need an x cubed up top in order to change the dx into a du. Now I have an x cubed here, so I'll be able to change it to a du. And you're like, well, what about the rest of the x's? Well, I have this x to the 8th here, and since u is x to the 4th, u squared is x to the 8th. So this would be a u squared, and this will end up being a u squared as well. So if you can see that clever algebraic trick, your u substitution takes you down here, and now we're just about done. We just have to find the table that matches this guy, 1 over u squared times the square root of, here it is, number 36. 1 over u squared times the square root of a squared minus u squared. Apparently, its antiderivative is equal to this mess. So I'll leave the -7/4 out in front and copy exactly what I see here, except in place of a, I'll write a 3, and in place of u, I'll write x to the 4th. And that gets me here. And then if you want, you can get rid of the parentheses by just multiplying -7/4 and -1/9 to get 7/36. And we still got the x to the 4th down on the bottom and the square root of 9 minus x to the 8th plus c. That's the idea for the extra credit problem. I guess we'll end this video here.